We're looking at solving distance problems. Distance equals rate times time. And this is a tough skill for a lot of people, but once you develop just a common strategy to help you figure out these problems, they become a lot easier as you just keep practicing and doing problem after problem. So let's go ahead and dive into this. The first one we have is a runner jogged at an average speed of 6 miles per hour on flat terrain and slowed down to an average of 4 miles per hour on the uphill sections. If the total distance covered was 20 miles, how long did the entire run take if jogging on the flat terrain took the same amount of time as jogging on the uphill sections? The difficulty with these problems is identifying what are we looking at? Like, what information do I gather from here? Do I absolutely need? What is important? So the first step that I would take is just set up a table. This just allows us to start to organize the information and really then translate that table into an equation, or in some cases like a system of equations if you're at that point. But let's just, so the first thing is we have distance equals rate times time. That's the information we're looking at here. Distance equals rate times time. Now in this scenario, what are we talking about though? We're talking about a runner that jogged on flat terrain and then uphill. So we have flat section that we ran on, and then we have an uphill section that we ran on. Well, from here, we can then plug in the gaps or fill in the gaps. We know that on the flat section, we ran 6 miles per hour. So flat rate is 6 miles per hour. 4 miles per hour on the uphill section. So rate for the uphill section would be 4. Total distance covered was 20 miles. How long did the entire run take if jogging on the flat terrain took the same amount of time as jogging on the uphill sections? So time. Time is the component that I'm really kind of struggling with. What do I call that? Because it says we ran a flat terrain, we ran on uphill section, we ran at a rate, but then it says at the very end, it took the same amount of time as jogging up and down. So I'm going to call that X because it says the flat terrain took the same amount of time as the uphill. So if I call that X, that's also X. If it took me 2 hours to run on the flat terrain, it also took me 2 hours to run on the uphill section. So the distance then, distance is equal to rate times time. Distance is 6x for flat. Distance is 4x for uphill. And we ran a total of 20 miles. So if I take the flat distance, that's 6x, and I add the uphill distance, that's 4x, I ran 20 miles total. So whatever mileage I ran for flat section, which was 6x, because if I ran at a rate of 6 miles an hour for an hour, 2 hours, 3 hours, that would give me my total mileage for the flat. Uphill, 4 miles an hour, 1 hour, 2 hours, 3 hours, whatever came out to xb, put those two distances together, you get 20. And then it's just 6x plus 4x is 10x equal to 20. Divide by 10, x equal to 2. So it says x equal to 2. That means that both the flat and the uphill was 2 hours each. So 2 hours. How long? Oh, good follow-up question here. It says, how long did the entire run take? The entire run. If I ran uphill for 2 hours, ran the flat section for 2 hours, 2 plus 2 is 4. So the total trip took 4 hours. Good problem there. Number 2. 2 trains leave a station at the same time, traveling in opposite directions. One travels east at a speed that is 12 miles per hour faster than the other train traveling west. In 4 hours, the trains are 384 miles apart. Find the speed of each train. What I always like to do with these scenarios is draw something out. So it says we have 2 trains leaving a station in opposite directions. So here's our station. We got one going this way, one going that way, east and west. So one's going east this way, one's going west. All right. One train travels east at a speed that is 12 miles per hour faster than the other train traveling west. We got one going east. The other is going west. The one going east is 12 miles per hour faster than the one traveling west. So I don't know how fast the one traveling west is, so I'm going to call that x. The other one then going east is x plus 12 because it's going 12 miles per hour faster. In 4 hours, the trains are 384 miles apart. Find the speed of each train. So this is a good start. Getting this visual of like, all right, I have a station. They're going 2 different directions. I have their rates But now I'm missing this time and distance components that I need to figure out. So this is where our table is going to come into play. Just like the last one, it's always good to draw tables, get a nice understanding of what we're dealing with. So we have distance equals rate times time. We have a train going east. We have a train going west. Let's start just piecing in the gaps here. The train going east was going 12 miles an hour faster, which we already talked about, so that's going to be x plus 12. And the one traveling west was x. In 4 hours, the trains are 384 miles apart. So they leave at the same time, and they both travel for 4 hours. The distance then is going to be time, or I guess I could say rate times time. It doesn't matter. Distance equals rate times time. But I'll just say 4 times x plus 12 for the distance of eastbound train. And then the westbound train went for 4 hours at a certain rate. After those 4 hours, so we snapshot after 4 hours, and this distance between the two is 384. So however far this train traveled, plus however far this train traveled, was going to be 384 miles. So it'll be 4 times x plus 12 plus 4x equals the total trip of 384 miles. I guess not the total trip, but the total distance between the two trains at that moment in time. Now it's an equation solving exercise. So 4 times x is 4x. 4 times 12 is 48. Plus 4x equals 384. Go through the solving steps a little bit quick. 4x plus 4x is 8x. Plus 48 equals 384. 384 minus 48. So we get 8x equals 336 divided by 8. X equals 42. It's really, really important in these problems that you don't just circle your answer and move on. Make sure you understand what is your answer. Is this the actual answer that they're looking for? It says find the speed of each train. X is 42. What is the 42 saying? X is 42. That means the westbound train went at 42 miles per hour, but the eastbound train was going 12 miles an hour faster than that. So that's going to be 54 miles per hour. So we have to identify both parts of the answer there because it says find the speed of each train. So those are the first two problems. Let's look at number 3. How long will it take a plane traveling at 500 miles per hour to overtake another plane traveling at 400 miles per hour if the slower plane had a 1 hour head start? So it's good to visualize, understand what's happening. We have a plane traveling at 500 miles an hour, and we have another plane traveling at 400 miles an hour. And what we're wondering is how long will it take this 500 mile an hour per hour traveling plane to overtake that 400 mile per hour traveling plane? So we want to know what is happening, like how long will it take it for it to catch up? And the slower plane had a 1 hour head start. So let's do the same thing. Let's set up a table. It's always good. Not going to hurt anything if we just start off with setting up a table here. We have the plane going at 500 miles per hour. We have the plane going at 400 miles per hour. The rate of the 500 hour plane is 500, 400. Now the time component. Time, the slower plane had a 1 hour head start. So if the fast plane, we'll call this plane the fast plane, if the fast plane was traveling for X amount of hours, how long was the slower plane traveling? If it's got a 1 hour head start, it was traveling for 1 hour longer. The fast plane left 1 hour later, so the slow plane is out there for 1 additional hour. So we could say 500x for the distance, and then 400 times x plus 1. And what we're wondering is when are they equal to one another? That's what we're trying to figure out. When are they going to be equal to one another? So however far the fast plane went, that is going to be equal to the slow plane of 400 times x plus 1. Distribute, so 500x equals 400x plus 400. And then I'm going to subtract 400x. So I get 100x equals 400 divided by 100, x equals 4. So it looks like we get an answer of 4 hours for the slow plane, or sorry, 4 hours for the fast plane to catch up. A good scenario there. So all three of these problems I just took a look at. I'm going to look at one more in this video. But all three of these problems were good scenarios because they're all kind of a little bit different, where you really have to understand what's happening and what the information that is being provided to us. So let's look at one more here. Finding numbers of denominations. A bake sale raised $960 in $5 and $20 bills. If there were 18 more $20 bills and $5 bills, find the number of each denomination. So we have a total amount of money being raised, $960. And those are being provided as $50 bills and $20 bills. And there were 18 more $20 bills and $5 bills. Now you could set up like a whole system of equations, but let's just not do that. Let's do just setting up a little bit more of a linear path, if you will. So let's see. Let me try setting up a table here I guess it's kind of, I'm trying to figure out an easy way to translate this over, because we're kind of dealing with like the same information twice, because we have the value here. But I have 18 more $20 bills and $5 bills. So if I have X amount of $5 bills, let's say, then I have 18 more $20 bills. And then my value for the $5 bills would be $5, and my value would be $20. Oh, I'm sorry. Why did I label that? This is the amount of bills. Value. And this is the amount. Okay. So the value, how much that bill is worth, and then the amount of them. And then we have the total, 960. So we could say that so this would be the total. This would be 20 times x plus 18. And then 5 times x, so we would say 5x, the amount of $5 bills, plus 20 times x plus 18 is equal to the total value that they have. So we have a big sale that raised $960, $5 bills and $20 bills. So there were 18 more $20 bills and $5 bills. So if there are X amount of $5 bills, then that means there are 18 more $20 bills. And each value is it's $20, so times the amount. And then this plus this is going to give me my total in value. And that's a solving exercise from there. So 5x plus 20 times x is 20x, plus 20 times 18 is 360, equals 960. So 25x plus 360 equals 960. So we get 25x equals 600 divided by 25. X equals 24. So x equals 24. That means that we have 24 $5 bills. Oh, sorry. $5 bills. We have 24 of those. And then we have 18 more $20 bills. So $20 bills is going to be 24 plus 18. And that gives us 42. So 24 $5 bills and 42 $20 bills. These problems are usually, I think, a little bit more reasonable for most students to get, just because it's not dealing with like these formulas of distance equals rate times time. But again, what I did is I set up the money. The confusing part is like, how do I organize it? That's why I flipped it accidentally when I was originally setting it up. But the setup here is we have a $5 bill and a $20 bill, just like if we had uphill section and a flat section. And then the value or amount would be the distance or the rate or the time, whatever component you want it to be. But the $5, I have X amount. It means I have 18 more than a $5, so X plus 18. The value of a $5 bill is $5. $20 bills times 20. It's like a mixture problem. That's what makes it a little bit difficult to set it up into a table, is because you're not sure how to organize it. But once you see it a couple times in practice, it gets a little bit easier. So, tough section though.